So, hi everyone. I'm Adriana, and I'm currently a postdoc at the Astronomical Institute in the Czech Republic under the supervision of Dr. Borovicka. And before lunch, I'll walk you through our work focused on modeling spectra of ablating meteorites. This data we collected during my PhD under the supervision of Dr. Matlovic. We have presented these laboratory experiments at several conferences before, but for those of you seeing them for the first time, let me quickly give a brief overview of what about was this project. So this was an ESA-funded project led by Communist University in Bratislava in collaboration with the University of Stuttgart, where we carried out our experiments between 2020 and 2022. A few other institutions were involved too: Natural History Museum in Vienna, Paris Observatory, and Aerospace Lab Honore. And a key idea was to simulate meteor ablation in a plasma wind tunnel using real meteorite samples under entry-like conditions, which were equivalent to an entry velocity of about 12 kilometers per second at an altitude of about 80 kilometers. So basically, we simulated slower meteors of asteroidal origin. Overall, we have tested 22 meteorites covering a wide range of meteorite types, from carbonaceous chondrites, ordinary chondrites, echondrites, iron meteorite, and stony iron meteorite. So a really pretty diverse sample set. And here we can see our some of our meteorite samples. So on the left, we have prepared meteorites before testing. Then we can see their ablation during testing and the remaining material after testing. And to capture very detailed emission spectra, we used very high-resolution Echelle spectrograph from the University of Stuttgart. And here is an example. This is from the Bilanga meteorite. And so we can clearly see that it gave us a really rich set of emission lines to work with. And the main goal was to, let's say, identify some spectral features that can distinguish between different meteorite types by looking at line intensity ratios and picking out some specific diagnostic lines. And this data then help us to interpret meteor spectra of asteroidal origin from our ground-based spectral observations. So here are our previous results where we focused on standard analysis method, where we just looked at the measured line intensity ratios. And one of the key result here was that we determined or identified clear presence of cyanoradical or CN emission. It was for the first time, and particularly in a carbon-rich meteorite. Results well reflect the real bulk composition from the literature. And these two emissions, hydrogen and CN emissions, are very important for us because they indicate presence of some organics and hydrated minerals. So they can help us to distinguish, for example, carbonaceous chondrites from meteor observations. However, the clear confirmation of CN emission in meteor spectra still remains very challenging due to the limited spectral resolution in the investigated region. In case of hydrogen, it's more straightforward. In addition, we also found correlation between line intensity ratio and real chemical composition for other elements as well. And in terms of identifying some diagnostic spectral features for different meteor types, we, for example, found that the relative intensity of iron, magnesium, and chromium can be used to distinguish between basaltic HED group of echondrites from other echondrites and ordinary chondrites. And also we found that, for example, the presence of nickel lines can be useful to distinguish between chondrites which contain nickel and echondrites which generally lack it. So this was a very brief summary. So we identified both major and minor elements in this laboratory spectra. However, refractory elements like calcium, titanium, and aluminum were absent. So they didn't fully vaporize under conditions we reached in laboratory. And this is actually consistent with previous fireball spectral studies. And as I mentioned, we determined some diagnostic spectral features for specific meteor types. However, to determine very accurate chemical composition or elemental abundances, for this is needed detailed radiative transfer modeling. And that's what I've been working on over last months during my postdoc. So I applied a radiative transfer model developed by Dr. Borovicka to our laboratory spectra. This model assumes local thermal equilibrium and includes self-absorption in optically thick radiating plasma. Three parameters include plasma temperature, column density of iron atoms, relative abundances of other atoms, and visible surface area of radiating volume. So the main goal was, of course, to determine relative abundances of all elements we found in this laboratory spectra, and to distinguish some differences between meteorite types or subtypes that looked, let's say, very identical in our previous line intensity ratio analysis. And this approach will also validate the model's ability to describe meteoric plasma radiation. So to achieve this, we fitted all 22 meteorite spectra with this model. We determined elemental abundances relative to iron, and then we applied ionization correction using this equation. This is very important to convert them to true elemental mass ratios that can be then directly compared with the real bulk composition published in the literature. And here in this slide, I would like to emphasize the critical importance of this ionization correction when calculating elemental abundances. So in this table, we can see on the left, we have some typical ionization conditions for low temperature component, and on the right, we have for the high temperature component of meteor plasma. And the values in bold represent typical observed lines in meteor spectra, so mainly neutral lines. In the low temperature component of meteor plasma. So only 6% of the silicon is ionized. And very similar situation is for silicon in high temperature component of meteor plasma. However, for elements like sodium and calcium, it's total element present. And same goes for the singly ionized calcium in the high temperature component, and also for the hydrogen. Here we can see that neutral hydrogen represents only a small minority. So as a result, neglecting their ionization leads to absolutely wrong abundances. So what does it mean? It means that it doesn't matter that in general we don't see these singly ionized elements in meteor spectra. We need to include them in the calculation of elemental abundances. And here are some our results. So from our modeling, we determined the plasma temperatures ranging from about 5,200 kelvins to 5,800 kelvins, which is slightly higher than what we typically see in meteor spectra. And we found that most spectra couldn't be explained by an optically thin plasma model. Instead, the emission was more consistent with optically weak conditions. And in terms in identify some chemical composition, when comparing our model abundance ratios to the real bulk composition, chemical composition of these tested meteorites published in the literature, we would expect this trend. So in ideal case, 1-to-1 match. However, what did we get? Surprisingly, our results consistently showed higher iron to magnesium ratio. So here we can see that there is a clear correlation. However, our results show that magnesium from our modeling is less abundant relative to iron than it should be, what we know from the literature. So for example, for most of the ordinary and carbonaceous chondrites, the real iron to magnesium abundance ratio should be between 1 and 2. However, from our modeling, we can see that the magnesium is between 20 to 40 times less abundant relative to iron. And similarly, we found, for example, chromium to be more abundant than it should be compared to its published values. And the same goes, for example, for nickel. And then we looked at more volatile elements like sodium and potassium. And here we can see that the discrepancy is even more striking. And the question is, how is it possible? So apparently something else is going on. And as I mentioned before, that under our laboratory conditions, we didn't observe any emission of refractory elements. So we started to suspect incomplete vaporization of other elements as well, which basically could skew the observed or calculated elemental abundances in favor of more volatile or easily excited ones. And then we also found one relevant study by Schaefer and Fegley, who modeled equilibrium vaporization for two of meteoritic material, for Ci chondrite and for eucrite, using some magma model. So let's have a look only for chondritic melt. Here on the x-axis, we have the fraction of the melt that has vaporized. And on the y-axis, we have abundance of sodium relative to iron for different temperatures. And here we can see clearly that for a fixed temperature, the abundance ratio of sodium relative to iron significantly increases when only a small fraction of the melt has vaporized. And this is exactly what we see in our results. So really high sodium to iron ratio indicating very early vaporization of sodium. And then when looking at a ratio of magnesium to iron, and when we consider from our modeling this abundance ratio for carbonaceous chondrites, where we found that magnesium was about 25 times less abundant than it should be. And when we interface temperature of about 1900 kelvins, which was measured by our colleagues from Stuttgart, this model assumes that only about 30% of the melt would need to vaporize to use such abundance ratio. And finally, if we look at more refractory elements like calcium and aluminium, we can see that at temperatures around 2000 kelvins, these refractory elements didn't vaporize. So results from this paper strongly support our assumption that incomplete vaporization occurred under laboratory conditions. And as I mentioned before, our conditions correspond to ablation at an altitude of about 80 kilometers. And in case of meteor spectra, at higher altitudes, we typically observe very strong sodium lines compared to weaker iron and magnesium lines. However, in lower altitudes, basically we observe that these lines become stronger. And so this paper also confirms the expected trend that volatile elements like sodium, potassium start to vaporize first, followed by less volatile elements, for example, magnesium, iron, and so on. And refractory elements like calcium, aluminium, and titanium remains in the melt, probably in the form of droplets. And we don't see them in meteor spectra, or only vaporize partially. And also how much each element vaporizes strongly also depends on the material type of the original meteoroid. Okay, so to sum up, our modeling of meteorite spectra showed that the radiating plasma had temperatures over 5000 kelvins, with emission rather corresponded to an optically thick plasma. And the observations result likely from differences in sample size and bulk composition. And the key finding here was that the vaporization was incomplete, and this explains the discrepancies between our modeled results of elemental abundances compared to the real bulk composition that is published in the literature. So that's all. Thank you for your attention.
Okay, thank you very much for your talk and also for keeping the time. We have time for questions.
Hi, thanks. That was really interesting. Are all of your modelling done based on the assumption of a velocity of 12 kilometers per second? Because real meteors can enter the atmosphere up to 70, and the kinetic energy is v squared, which would allow a vastly amount of energy, greater energy to be available for the vaporization in real examples. So does your modelling include higher velocities?
No,
Right.
no,
Okay.
no.
Thanks for the talk. On the optical thick plasma, could you iterate a bit on the absorption that you must see there?
If we can...
You see, let's say if you have optical thick plasma, you
Yes.
will have absorption lines to
Yes.
observe. Can you maybe explain a bit? What do you observe actually? Which absorption lines do you observe? What?
Okay. So basically, it's typically for very strong lines of sodium sometimes for magnesium and also for some of the strongest iron lines. So they are very strong. And when we include also self-absorption, it's one parameter for this, then we can get much better fit. And
so I'm asking that quite a number of people, including us, we do the simulations. So you're saying we have to include the absorption lines in our simulations, right? That's what I have to learn from your summary.
yes, it should be, in general, it should be considered for all meters brighter than, I think, if I'm not wrong, for magnitude, +4 magnitude.
Okay.
One more question.
Hi, thanks a lot for your talk. One question, do you use subsonic or supersonic conditions in the plasma chamber?
Jirı, can you help me? You have more information.
The over the sonic, I'm sorry, supersonic, yeah. So, but in details, yeah, we need to maybe ask colleagues in Stuttgart. Yeah.
All right, thanks.
Okay, thank you, Adriana, again.